We spent a lot of time talking about the search problem, looking for things. And so now let's talk about a really important case where our data has not just one dimensions, but many. So before we get there, I'll just summarize what we've seen in terms of sets and maps. We've seen two key techniques. We have a hash table-based approach and a search tree-based approach. And each of those required something about our keys. So hash tables, we had to be able to hash our keys. Search trees, they had to be comparable. We've also seen two really special case implementations. One was the data indexed array. So this is when all the keys are small. You could just use an array, as we saw in our tries lecture and also in our hashing lecture. And then with if our keys are strings, well, then we can use what's known as a trie. Saw that in an earlier lecture. And essentially, by knowing something special about my keys, I can get better performance, especially on operations that interact with those keys in a special way. So for example, prefix finding for tries. So today, we're going to talk about another really important special case where our keys are multidimensional. And we'll see, just like we're tries, we have these new operations like longest prefix of or keys with prefix. With multidimensional keys, there'll be similar special case operations that we will be able to support efficiently. So what do I mean by that? Let me give you an example. So let's say I have a bunch of objects in space. So you may recall these from an earlier project in this class. Here are a bunch of little suns orbiting one big sun. And let's say we want to know what are all of the objects in space that are inside this green rectangle, which I might call a 2D range search or a 2D range finding operation. So in this case, it could be which objects are in the rectangle or just how many are there. Okay. Another would be nearest neighbors. So I could say, what is the closest object to this space horse that I just added? And it's right here by the hoof. Okay. So we could do this with our normal set implementations, either hash tables or binary search trees. And so let's just think about the hash table approach first. So let's say that our set is stored as a hash table, and the hash code of each body is given here, where this is just pseudocode. So we take the x position, which is a double, and we compute its hash code. We multiply that by 31 to the fourth, and so forth. Okay? The exact hash code doesn't much matter, but just to let you know, it's like a normal hash code. So question for you is, how would you implement nearest? So if you added it to a hash table implementation, what would you do? And what would be the runtime? So when I say how would it be implemented, it's just basically thinking mentally like what would have to happen? And then runtime, tell me what that would be. Okay. So the important point here is that if you have all these objects stored in just a regular old hash table, then the nearest operation, what you have to do is just iterate over every single item. And that's because the location of each object, that is the bucket that each one lives in, is effectively random. So we don't know which buckets to look in our hash table. So we just have to iterate over all the items, and the runtime for that would be theta n. Okay. So what we're going to try and do is do something a little better, and that will bring us to many different solutions. So that's the setup, though. That's the important thing today. We want to support operations like this that are special to objects in space.